Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 47 and where we try to understand the nuances of oscillators and that operating at cryo temperatures. Where these oscillators are used, you must be aware that you need to have a local oscillator available within the readout circuitry where you mix the incoming waveform from the qubit and the local oscillator, and the local input should be there, and that is where oscillators are used. Apart from that, they are also used as clocks for synchronous circuits within the quantum system. So, we will look into the basics. Those who are not initiated in this domain, we will look into the basics and the type of oscillators which we generally have, and then we will look into the performance limitations of room temperature oscillators. We look at the challenges of cryogenic temperatures, a performance matrix, jitter and phase noise, cryo-oscillators, and we finally come to advantages and trade-offs and application areas of cryo-oscillators. So, again you need to know the motivation for designing it. There has been a lot of study on oscillator design for many decades now, and many of the oscillator designs are stable and have been there for quite a long time with very good performance at room temperature, of course. What is missing is at relatively low temperatures, very low temperatures, the oscillator characteristics is still not very clear, its stability is still not clear. Similarly, the performance limitations are very large when you operate also at extra low temperatures, right. This is one area where you need to take care of in terms of both the phase noise, the jitter noise, and try to optimize the performance matrix. Now, all of you are aware of, I will quickly go through it, that basically an oscillator is a one which converts a direct current from a power supply to AC signal, which basically means that if you have an input signal, even if there is no input signal and if there is a small noise, right, that noise can be actually amplified into an AC signal, a stable AC signal, and the energy for that comes from the power supply which is connected to the oscillator. Now, generally an amplifier which uses a positive feedback without any external input signal is defined as an oscillator. So, if you remember that when you have negative feedback, you write down the gain with feedback to be equals to A upon 1 plus A times beta, where A is the gain, open loop gain, and beta is the feedback ratio. So, when the feedback ratio becomes larger and larger, this starts to fall down, right. This is for the negative feedback, right. For the negative feedback we get it. For the positive feedback we get a negative sign here which makes it go higher. With feedback it goes higher. Now, so basically you need to do a positive feedback and with 0 or 360-degree phase shift, and when you are able to do that, you sustain a positive feedback and the signals get superimposed, and therefore it acts like an amplifier over a period of time, right. Now, the frequency of the output wave may be actually fixed or varied depending on the oscillator design, which is of course the way we design an oscillator is something like this, that if I want a fixed output frequency of the waveform, then we define that frequency in that manner, or if we want that it should be a tunable frequency, then we can actually have a tunable frequency based oscillator, right. For example, there are many oscillators which are tunable in nature, right, in the sense that by changing the values of the passive element within the oscillator or even the active element within the oscillator, you can actually change the frequency of the oscillator, right. Where they are used, typically they are used in clock generation. Whenever we talk in terms of design aspects, they are typically oscillators are used in all clock generation issues. But the problem with clock generation is that if you have an on-chip clock generation, since the activity factor is very high for a clock, the power dissipation levels are very high. And that is one of the major disadvantages of oscillator, or maybe a challenge of an oscillator, that since it is a clock and the clocks have shear transitions, we are certain that the amount of power dissipated by the clock will be relatively very high. And since all these work at very hard sort of power budgets, this clock generation will give you relatively a larger value of power dissipation. They are also used in communication systems over a period of time. They are used in communication systems for generation of the clock. They are generally used for even value of systems, even value of signals to be generated peak to peak. Now, the problem with clock generations are that there are multiple problems with clock generation, and there are certain challenges which you face when you do challenges when you face with clock, and they are jitter and you have skew. Within skew you can have positive skew and negative skew, right, and then jitter will be available with you. We will come to that if as we move ahead, but these are the few challenges which you face when you design it for the purpose of clock. You also are aware of that for oscillation to be a true, the Bar-Consensus criteria has to be met, implying that the unity gain loop has to be there, right. Unity gain loop, this is known as the loop gain. A into beta is defined as the loop gain, right. This is the loop gain. Now, this loop gain has to be equals to 1, which means that if you have A upon A minus 1 beta, A beta, right, 1 minus A beta, then this A beta equals to 1 means the denominator tends to go to 0, and therefore, my AF tends to go to very large value, right. And that is the meaning what is known as the unity loop gain tends to make your feedback, post feedback, the amplification to be very large, right. Now, the total phase shift should be around 360 degree, which is but obvious for a positive feedback to be true. Typically, oscillators are divided into 3 sections: amplifier circuits and feedback circuits. So if you look at a typical block of an oscillator, you will see this to be as the amplified feed forward path, and there is a feedback path, right. This is a feedback path. This is the feed forward path, and this is feedback path. This is the output, and you have an input here, right. And this is the general diagram, like any negative or positive feedback path will have this block diagram available with you. What are the types of feedback? There are 5 types of feedback, but there are others, but for this purposes, for this course, this is sufficient to have it. One is known as the RC oscillator, which is there. Then you have an LC oscillator, right. This is RC means you have a resistance and a capacitance in the oscillator. LC oscillator basically means inductor and a capacitor. Crystal oscillator, you have a ring oscillator, and you have a relaxation oscillator, right. The whole idea is in oscillator is that you store energy at one place and you try to dissipate the energy at other point, right. And if this is a cyclic process which repeats after every cycle, then you will have an oscillator. Just as an LC oscillator, you will see you will be storing energy in form of energy in inductance, right. Or let's take an RC oscillator, you will be storing it in the capacitor as a half CV square, and then you will be dissipating across resistor, so on and so forth. Every time you switch back and forth, you will have this oscillation frequency, which will be stable oscillation frequency available with you. So, the general idea of an oscillator for any oscillator is storage of energy and dissipation of energy to the external circuitry. Now, what are the performance limitations of room temperature oscillator? The problem with oscillator, one of the major problems of oscillator is phase noise, right. Typically, at room temperature, the thermal noise dominates, right. You remember if in my previous talks, I had shown to you that the thermal noise that which we have already seen is proportional to root of kT, where T is the temperature and K is the Boltzmann constant. And therefore, my external temperature, my thermal noise is directly proportional to temperature. So, higher the temperature or higher the ambient, more will be the thermal noise. And therefore, what happens is that with this thermal noise being added to the system, the signal to noise ratios SNRs degrade, right. That is one thing. It also leads to the broadening of the spectral line width, right. So, spectral line width broadening, and therefore, the signal purity is lost, which means that you are, what do I mean by that? Let us suppose I have a signal which I want to generate at 40 megahertz. Let us suppose my peak frequency or the center frequency is 40 megahertz. But I also start, when I design the oscillator, I also start getting some noise or some oscillations at 39, 38, 37 megahertz, right. That is not a, so high, more is that sideband oscillations coming into picture, more degraded your signal purity will be. And that is the reason we try to maintain very least value of thermal noise in this case, right. And therefore, what it does is that it limits the resolution of any communication, right, and that is the problem which you will face. The second aspect is you will have increased flicker noise, right. Your flicker noise is basically also referred to as a 1 by f noise, and it is an inversely depending on the frequency. So, higher the frequency, lower is the noise. So, if you are operating at relatively low frequency of the order of few kilohertz or so, You will also have an increased flicker noise. Not every time you operate at very high frequencies, but fortunately for quantum computing purposes, these operate at few gigahertz. At these high frequencies, there is a reduced flicker noise at cryogenic temperatures, but at room temperature, they play a major sort of a degrading effect on the oscillators. Finally, you need to integrate this oscillator with the system, right? And that is the challenge which you come into picture, because this oscillator output frequency has to be matched exactly with the impedance has to be exactly matched with the load, so that the power is transferred very easily from the oscillator to the external source, especially the plus. Moreover, oscillators actually, as I discussed with you, are primarily responsible for clocks, for generating clocks, but the problem is these clocks will be routed through long interconnects across the network, where the chip is there. When this happens, you will also have many major challenges related to jitter and noise. Now, when you want to work at low temperatures, what are the challenges which you will face at cryogenic temperature? That there will be you require a very low phase noise at quantum computer. Otherwise, and you can understand the reason. I have already discussed it earlier, that your noise floor will be slightly higher as compared to your signal floor, and therefore the overall fidelity of the computer network which you are trying to do, the quantum network which you are trying to do, will be compromised. Now another problem is that the oscillators which operate at cryogenic temperatures will actually showcase a very large fluctuations in their parameters with temperature, and there are no mature device level models which are available at this stage in order to substantiate the changes which is happening due to the temperature induced effects on the devices. So, that is a major challenge which you will face. Similarly, obviously the power dissipation is a challenge for all practical purposes in all cryogenic devices. Let us look at the performance matrix of an operational amplifier. Now, as I discussed with you, there are primarily four performance matrix, and these are basically your phase noise, your power consumption, your tuning range and sensitivity. Now, thermal noise actually reduces at cryo, and that basically improves my phase noise. So, that is a good thing about cryo. I do not have to do an extra layer of modeling in order to understand that. It is very straightforward and simple. The thermal noise reduces. Therefore, the one challenge therefore comes into picture is that the total noise is dominated by the flicker noise and RTS, the random telegraphic noise. These noise are then become much higher as compared to a thermal noise, and that affects your output power matrix. Now, power dissipation, again, typically you need to reduce the desirable quantum platforms, requires Kelvin range. Tuning frequency basically means that if you are tuning basically it means that how much frequency you are tuning your oscillators to, right? Why? Because these oscillators are also used in PLLs, phase lock loops, as well as for adaptable readout circuitry, where the frequency needs to be changed, say from 5 gigahertz to 5.5 gigahertz, right? So, you need to have a large tuning range for the oscillators to work properly at such high frequency. The last point is of course sensitivity to performance to variations, and that has to be kept at the bare minimum. Now, quickly go through the jitter and phase noise before we enter into the oscillator. Again, not part of the course, but needed to give you a brief insight so that you are able to connect the dots properly. Jitter is basically the deviation of the clock edge from an ideal position, right? That is what the jitter is all about. And the jitter is measured in the time domain, and the phase noise is measured in the frequency domain. So, what do so if you look at the PSD, the power spectral density here, right, you are plotting the power density versus frequency, then you will see at f naught you see almost delta f is FWHM, I mean a full width at half maxima, right. FWHM is what you are getting here, and that is delta f which you see. So, we define a term delta f by f naught as the Q factor, right. Smaller this value, right, means if this Q is, which means that ideally delta f should be, so let me give you an idea here. This should be, this should be f0 by delta f, which basically means that your delta f should be as small as possible to make the Q factor as large as possible. Selectivity is measured in a very good manner. Now, the problem is that the jitter which happens is the deviation of the clock edge. So, you will have an ideal clock edge, and suddenly because of jitter there is a deviation of the clock edge, right. So, what are the sources of phase noise or jitter? Primarily power supply noise is one of the major problem areas for jitter. Then you have a ground bounce problem, right? And there is a channel noise. Channel noise comprises of three noise: thermal noise, flicker noise, and short noise, right? And these are all coming from the channel of the active device which has been there in the oscillators. I will not go into details of this at this stage. Please go through it otherwise or in some other course. But these are noise figures which come primarily because of device level characterization, right? Short noise is because of tapping, retrapping. Flicker is because of quasi-static movement. Thermal noise is primarily because of thermal vibrations of the lattice, which results in these noise, right? And these are all reflected onto the phase and jitter noise. So, this is an example which you see in front of you is a cryo oscillator. Where they are fixed, they are somewhere in between the local. So, they feed clocks to the local oscillator here. These are all local oscillators which are there, right. So, this is my readout circuitry and this is my driver circuitry. The driver circuitry drives my demux and tells which of the qubits you need to activate. That information is going to the mux here. The mux then sends the signal output to the low noise amplifier, which we have already studied, which finally goes into the local oscillator and mixes with the clock signal here. This goes to a low pass filter ADC, and then there is a digital output here. The digital output is compared with the input, and if there is a change, the change is actually given to here, and the reverse happens in this case and goes to the demux. The oscillator which sits here sits at somewhere around 1 to 4.2 Kelvin, and this is one of the standard LC oscillators which you see here. And these are all like there is no change in the architecture of oscillator because they have been standardized and done, but this is simple RC oscillator which you see, and the energy basically which is stored in the capacitor and inductor basically. So, these cross coupled transistors M1 and M2, these are all cross coupled inverters, right. So, this is where the positive feedback comes into picture. You see, I am giving an in signal to the gate, current is flowing through this NMOS, this current develops a voltage here, this voltage feeds this M1 and so on and so forth. So, this gives you a positive feedback, and this is where you store the energy for the circuit, and this is where you are drawing VDD power rail from the top, and this is the ground here, right. So, typically this is basically what is known as a class D or a F2 oscillator schematic, this schematic which you see in front of you, and this actually shows to you that the impedance levels, common mode impedance levels are much higher at M2 as compared to towards differential mode. The common mode are much higher as compared to differential mode. However, they will be able to give you substantially large amount of resistance oscillations in this case. Now, this is what I was discussing to you. You have two sets of capacitors here. One is CC here and another is CD here, this one, and they are primarily used to adjust the fundamental and second harmonic. Second harmonics, what does second harmonic mean is fundamental is basically where your oscillator frequency peaks at a particular frequency, that is a fundamental, but you can't help but to generate secondary harmonics which will be to the left and right of the single harmonic, right, and this gives rise to asymmetric rise time and fall time, right, and therefore there is a high flicker noise and high phase noise comes into picture. There is sometimes also an availability of, there is also sometimes a generation of third harmonic. Now, this is primarily symmetricity of rise time and fall time is maintained in this case, and if you superimpose first and third harmonics, then we get a much less phase noise. So, there is a technique available where you can actually superimpose two harmonics in order to reduce the phase noise, and that is typically used in a cryo oscillator for all practical purposes. Here we are again not talking about the variability issue between M1 and M2. The variability issue has not been taken care of here. I am assuming that both M1 and M2 are perfectly symmetrical in device structure and their transconductance are exactly the same. So, therefore, for the same amount of voltage given to the gate of these transistors, I will get exactly the same change in the output drain current, right, and therefore, the voltage levels are all symmetric on the left and right hand side. Okay. Now, the CC and CD are primarily used to adjust the fundamental and the second harmonic resonances of the oscillator, right. Now let's take up this idea here and let's look up what the idea here is. Now, there are two types of resonance which will occur. One is a common mode resonance, right, and there will be and what happens is that this is 3 dB of the phase noise limit typically around. If you have phase noise limit which is actually in the cross coupled LC oscillator, then your 3 dB, it will be around 3 dB bandwidth which will come to that, the 3 dB voltage difference will come into picture. Now the flicker noise, so ideally this is used for flicker noise reduction, right. Now the flicker noise upconversion of differential pair transistor is also reduced. What does it mean? That since you are doing a positive feedback, the flicker noise component will also be added up, right. So for every iteration you go, the flicker noise gets added up in a manner which is additive in nature, and therefore if you don't control it, will go beyond a point and you make your device unstable. So what you try to do is that you try to do an upconversion of the differential pair. So when you have a differential pair, the noise gets cancelled out and you typically have a reduced value of flicker noise available to you. Now it is also understand, of course, if you are operating at cryogenic temperatures, we should know how the devices, each of the passive and active elements of these structures will behave in a proper manner, right. And therefore whenever we do a simulation at cryo, there is always a difference between the theoretical value and the measured value of the cryo oscillator. Now if you look at the if you compare this with 300 Kelvin, so the right hand side, if you look very carefully, is basically the plot of the phase noise versus frequency, right. And you can see that the phase noise starts to actually, in negative sense, goes on increasing as you make your offset frequency larger and larger. And obviously at 4.2 Kelvin it is relatively lower as compared to 300 Kelvin. As you can see here, this is 300 Kelvin, this is 400 Kelvin which you see, and my x axis is in the log scale, mind you, right. So it is not actually linear, its x axis is, it is not linearly falling, but it is falling nonetheless, right. It is always reducing. Expected also, as the frequency increases, your phase noise component becomes higher and higher because of reduced thermal effects. As we have known, and there is reported in many papers, that moving to 4.2 Kelvin actually, the short noise contributes to 90% of the total phase noise, right. And this is primarily due to substantial reduction of thermal noise at such low frequencies, which means that at cryogenics you have to be very careful about the short noise sort of modeling, right. What are the advantages of cryo-oscillators? There are certain advantages of cryo-oscillators, and they are primarily used for reduced noise floor, improved Q factor is there. There is obviously an enhanced carrier mobility at lower at cryogenics temperature, and therefore it helps you to improve the transistor transconductance. You have better frequency stability here, right. Lower temperature variation leads to more stable oscillation frequency. Then of course there are compatible with CMOS processes and systems, so system integration is seamless with readouts as well as with low noise sensors on the back end. Then of course you will have reduced power consumption by operating at 4.2 Kelvin at very reduced value. So these are the advantages of sort of cryo oscillators. But let us look at the trade-offs of cryo oscillators. Now the trade-offs are, you typically have larger device parameter shifts, right. And this is primarily happening at low temperature. You might have a threshold voltage transconductance shifts taking place. So you might not be able to predict a priori the amplification factor which is happening. Similarly, there are very limited modeling tools below 77K, right. There is a research going on, but still very stable modeling tools are not available below 77K. Another major issue is that passive component variability happens at low temperature and become very unstable in that sense. Then of course one major problem, and this is a very practical problem, is packaging and thermal stress at low temperature. Packaging is a big issue. So if you have a standard ceramic packaging, they might not be substantially stable at such cryo temperatures, right. And we need to be very careful about how we do packaging at such a low temperature. Of course measurement systems are very complex in nature, and as I discussed with you earlier also, integration complexity is there. These are the few application areas I have noted it down, you know, where we have been doing it for past few lectures. They are used in quantum computing, used in building blocks, space and satellite systems, RF and high sensitivity sensors. So let me recapitulate and give you the brief idea about what we did till now. We looked into the concept of cryo oscillators. We looked into oscillators here, right. And then after looking into oscillators, we went into the domain of how oscillators, what are the challenges of oscillators at room temperature and at cryo temperature. We looked into a basic structure of an oscillator at cryo temperature, and that was primarily a D2 oscillator. After looking into that, we went ahead and discussed about the functionality of it and how to reduce the phase noise at such a low temperature. We looked into the concept of phase noise, thermal noise, right. We looked into the concept of noise also. So, we looked into the concept of noise, where we looked into phase noise and we looked into the concept of thermal noise, right. Then after doing these noise elements, we using the feedback and methods, how was the noise suppressed, we came to know that. And then we also learned that the first and third harmonic can be actually mixed up to reduce the noise. So, noise is one of the major concern when you design an oscillator in this case. That finally, we ended up looking into various figure of merits of an oscillator and also looking at various application areas of oscillator in a sense. Where will be this where will be this you will be helpful for learning this oscillator will be for all local oscillator design at for designing the clock frequency or the clocks internally. For feeding the clock to the local oscillator you will be requiring such type of cryo oscillator working at ultra low temperatures, right. So, with this I will stop today's lecture and we will continue with next readout circuitry component in my next lecture. Thank you.